Newton's second law of motion. From Newton's first law, if the resultant force is 0, then the object will, of course, remain at rest, or the state of motion will be unchanged. Or put otherwise, Newton said, if an object is at rest or moving with a constant velocity on a straight line, it will remain unchanged unless an external unbalanced force acts on it. Simply put, if I have an object, if I have an object here, this object will remain there unless there is an applied force on this object. And that applied force, if this surface has friction, that applied force must be more than the frictional force. If that applied force is equal to the friction, if the applied force is equal to the friction, therefore, the object will remain at rest. So for this object to experience motion or an acceleration, there should be a resultant force, and this object will move in the direction of that resultant force. If the applied force is increased and it overcomes the friction between the surface where the object is resting, this object will basically accelerate in the direction of the applied force. This object will experience acceleration in the direction of the applied resultant force. That is what Newton said in his second law. And Newton realized that if you take a truck, a big truck, and you take a mini car, the force required to produce acceleration here will be big compared to the force that you need to apply to push a small car. Now, I hope you appreciate that acceleration is directly proportional to the resultant force. So let's have a look at this scenario here. If the resultant force is 100 Newton. We expect acceleration 1 if F1 is 100 Newton. But now, if F1 is 100,000 Newton, if F1 is increased to 100,000 Newton, we expect acceleration that will be far greater than acceleration number 1, because the force here has been increased. So an increase in the applied force causes an increase on the acceleration. That is a direct proportion relation. And that can also be presented on a Cartesian plane This can be represented on the Cartesian plane in that form, whereby you have your force here in Newton, unit for force, and you have your acceleration here in meters per second squared. That's what you have. He also realized that from where we have here that the acceleration is inversely proportional to the mass. Now, meaning that when the mass is big, when the mass of a lorry there compared to the mass of this mini here, so the mass is big here. If I apply this force on this, that will produce a particular acceleration. But if I take that big force and apply the big force here on the mini car will accelerate faster than that force. So you can realize that acceleration is inversely proportional to the mass. An increase in mass causes a decrease in acceleration. And that can be illustrated by this here. So we'll have our mass here in kgs, and we will have acceleration there in meters per second square. Now let's go back to a previous diagram here. Now, as the force increases this way, the acceleration, the force increases there, the acceleration also increases. And the mass is constant, of course. Now, if I look at this coordinate here, it will go down there and it will go down there. But let's go and have a look at the next picture here of invest. Now we will have the mass increasing. Now, mass, let's say the mass one here has that acceleration, which is a bigger number up there. Let's say 1, 2, 3, 4, 5, 6, 7. Mass one corresponds with 7. X and 7 up there. Let's go to mass 4 here. You can see X is 4, Y is 3. Let's go to this one here, 2, 3, 4, 5, 6, 7, 8. X is 8 here. And then our Y value will correspond to 2 there. Now, as the mass increases, the X value increases here, the acceleration becomes small when the force is constant in any way. Now, we have case 1 and case 2, which results into the force is equal to MA, but this is supposed to be the net force, the resultant force. The resultant force is equal to MA, and this constitutes Newton's second law of acceleration. That constitutes Newton's second law of acceleration. The most important thing to observe here is that the sum vector of all the forces involved should give you a resultant. If the resultant is equal to 0, therefore, there won't be any acceleration by Newton's first law. Now, let's look at example here where we can say, let's look at, let's go to the next page here. And then we look at this body here. Let's get this body here. Now, let's say this body has 8 kg. The mass is 8 kg there. And there is a force applied in that direction. Let's increase that force there. There are two things we need to have a look at here. One, is there friction where the object is resting, or is the surface here frictionless? Now, if you are given that you have 0.05 as static friction here, then we can get that we can get the friction if we are given the coefficient of friction. The coefficient of friction is 0.05 multiply we have here we have the normal going this way. We also know that we have the weight going that way. Those two must be equal. Now, let's label that. This will be the weight, which is equal to mg, the mass multiplied by gravitational acceleration. And that will be the normal force, which is equal to the weight. And this will be the frictional force, not net force, frictional force here. And then this, we can take it as an increased applied force. Now, this object will basically move to the right. This object will basically move to the right or east. Now, here the mass is 8 kg and the gravitational acceleration is 9.8 meters per second squared. We need to multiply that to get the frictional force, which is facing west, against the applied force. 0.05 times 8 multiplied by 9.8. That will give you 3.9. 3.92 Newton. Now, we said that we can calculate the force here if we are further given. It is always wise to write down the given data. And then we are also given that the acceleration is 2 meters per second squared. It's facing east in any way. Given that data, we say acceleration is 2 meters per second squared. The mass is 8 kg. F is, of course, unknown. We don't know what's the applied force, but that can be calculated because we say F resultant net force is equal to MA. Now, what does this mean? It means the applied force plus the frictional force is equal to MA. Now, these quantities here are vectors. The applied force and the frictional is always opposing, which is negative 3.92 Newton. And the mass is 8 kg, while the acceleration is 2 meters per second squared. And that gives us 16 Newton on the right. And then the applied force, if we transpose the 16 here, will be 16 Newton plus 3.92 Newton. And that will result into 19.92 newtons. That will be the magnitude of the applied force. And this is easterly. Hope you got that. Now let's look at another scenario where you are given an object and this object here is experiencing a force. The object experiences a force. This object experiences a force in that direction. Now, I hope you appreciate that there is an angle here. There is an angle there. Let's say this angle here is theta. And theta here, let's say that is equal to 30 degrees. And then here you have an applied force. Let's say this is 50 Newton applied in that direction. Obviously, if the surface as friction. Friction will be in that direction. Now, and if this object here has mass of, say, 10 kg here, let's say 5 kg, and the frictional force here let's say the frictional force here is 10 Newton. The frictional force is 10 Newton. Now, the challenge we have here is that the object will accelerate to the right if and only if that F, the cos of theta, is greater than the frictional force. That therefore we will experience a resultant force. So we need to get this force here, meaning that FA has to be broken into horizontal and vertical component. This will be the vertical component, the horizontal component of the applied force, and that will be the horizontal component. The horizontal component can be given by the sine trig ratio. This will have the cos trig ratio. So Fx will equal to, the force there is 50 Newton. And the cos of an angle theta, which is 30 degrees. So that is 50 Newton multiplied by 0.866. Let's see, that will be 50 multiplied by 0.866. And that gives 43.3 Newton. And 43.3 Newton facing east. So we can get the resultant force for us to get the acceleration will equal to the resultant force over mass. For resultant force, we'll have (43.3 Newton minus 10 Newton due to friction divided by the mass of an object. That will result into 33.3 divided by 5 kg. On your calculator, that will be 33.3 divided by 5, and that will be 6.66 meters per second square. That will be the produced acceleration of an object. Now, we have to look at numerous situations that we might get in the exam. Surely we should get. Let's look at an object on an incline. That. And we have an object there. We have an object here. Have an object there. That's an object there. You can realize that this object is on a tilt. We have an angle there, let's say alpha. Can give it a value there, let's say 45 degrees. Now, there are a number of things that we have to look at here. One is that this object has its weight perpendicular there to the surface, the inclined plane. But on the other hand, we will have that which is parallel to the plane there, and now, if this is a right angle here, by similarity of figures here, this angle here will be 45, and this will be the weight multiplied by the cos of theta. And this one here is opposite the angle here. This one will be the weight multiplied, not equal to, multiplied by the sine of alpha. When this one here will be the weight multiplied by the cos of alpha. Now, let's say the weight of this object is 2 kg. And this object will basically experience a downward force if the surface is frictionless, and this component of the weight causing it to go down will equal to that. Now, we know the weight. The weight is the mass of an object multiplied by its gravitational acceleration. Here it will be mg, the sine of theta, which is equal to the force that is parallel to the surface where an object of 2 kg is resting, and that will give us 2 kg multiplied by 9,8 meters per second squared, and the sine of 45, which is 0,7, and if we multiply that out, will be 0,7 times 2 times 9,8. That's 13,72. That will be 13,72. It means this object here will experience a force of 13,72 if and only if the surface is frictionless. If and only if the surface is frictionless. If the surface is rough as friction, suffering friction, and the friction will always oppose the applied force or the force experienced. So we will have to get the resultant, meaning that we'll have to subtract. Now, if we have to write a free body diagram, we will have something like this. Whereby for the surface which is frictionless, we will have that force there. We'll have the normal here. And then we'll have our weight there. We'll have the normal M, and we'll have our weight down there. That's what we'll have. There's no applied force. If we had an applied force going this way, we will have the applied force going there. And then this will be W, the sine of theta. W, the sine of alpha, which is mg, the sine of alpha. And this one will be the normal. And this one will be mg, the cos of alpha. Now, the scenario will change if we had an applied force going down there. This is going down, sliding down the slope due to gravity. If you had an applied force, we'll put the applied force here. The second case we will have will be this one here. We have two objects there. And these objects are joined there. Let's see that. These objects are joined them, and then we will have and we will have an applied force in that direction. Now, let's give content to it. Call this mass 1, call this mass 2. Now, you can further say the mass 1 is equal to 200 kgs, and the mass 1 is 1,000 kg, which is 1 ton. And there is a force applied here of 760 Newton. And this surface here is rough. It's on the rough surface, meaning there is frictional force experienced by the two objects. And if you are given that the coefficient of friction, of kinetic friction, of course, is 0.3, we can calculate if you are challenged to get the acceleration and the tension. The challenge here is to calculate one, the acceleration of the system, and the tension the tensile force here, tensile force, The best way is first to get the frictional force, the kinetic friction there, and the kinetic friction will equal to the coefficient of friction multiplied by that, and then that will equal to 0.3 multiplied by, for the mass one there is 200 kgs, which is mg, of course. G is 9.8 meters per second squared. And for the green mass there, the kinetic friction will equal to 0.30 multiplied by 1,000 kg multiplied by the mass, the 9.8 meters per second squared. Let's have a look here. We start with mass 1, 0.3 times 200 times 9.8. That will equal to 588 Newton. And then here we will have 0.3 times 1,000 times 9.8, and the frictional force will be 2940 Newton. Now, if you look at what you have here and what you have there, is basically more than what you apply there. So basically, acceleration here will be 0 meters per second squared, because applied force is less than the offered static friction, kinetic friction. So that's what is going to happen here. Now let's have a look at another case where you have no, before you go to the next case, let's try to get the free body diagram for the objects there. For the first one, we will have for body 1 and for body 2. Now, we will have 1, the obvious and the weight there. This should be equal. And then here you will have we'll have the tension, and here you have a frictional force. And then this will be 588 Newton. And then the applied force there is not felt. Here, you will have the applied force. And then here, we'll have Newton there. And then here, we'll have the normal. While down here, you have the weight. Now, the applied force is far less than the friction. The applied force is far less. So make it small. That's what you have here. That's what you will have. So basically, this one experiences that. It also experiences the tension there. That suffices. Let's look at another scenario here. Where we have an object here. And another object there. And you have you have a pulley there. We have a frictionless pulley. Here. If you have a frictionless pulley there. Now, let's give it content. And say here we have 7 kg. And then up there you have 3 kg. Obviously, we will have tension there, with the same tension there. And if we have an applied force west horizontal applied force and then the whole system moves that way to the west. Now let's first draw force diagrams here, or free body diagrams for, let's call this mass A and call this the mass B. Now for A, we will have the obvious weight, and we have the weight here, and that mass equal to the normal there. And then we have the applied force in that direction. And let's say this surface offers friction here. If it goes that way, we expect friction to oppose. We also expect to experience the tension. So we basically have five forces there. You can name them. Here we have the tension. Here we have the tension. And then here we'll have the frictional force due to a rough surface there. And then here we'll have the applied force. That's what we have. Let's look at body B there. Body B will have these forces acting on it. The nice part about body B is that it will only experience the tension and the weight. Now, This will be a tension. And then this will be the weight. Which is equal to mg. Now, let's do our analysis. The object is moving this way. Here, it means that the tension is greater than the weight. Therefore, T minus mg, that gives us ma, the acceleration that the system will experience going this way. And for this one here, we have the force, applied force is bigger, is greater than the tension and the frictional force. So, meaning the applied force minus the tension plus the frictional force will give us MA. Now, if you are given the coefficient of friction as 0.1, you can get the friction there. Now, things to note is that T is common. Acceleration is common for the system. Therefore, you have equation 1. You have equation A or 1. And then you have equation 2 there. You have the 2 equations. And these equations can mathematically be solved simultaneously. Let's say you are given here the applied force was 2,000 newtons. You will substitute that for 2,000. This you don't know. This you can calculate because you are given the coefficient of friction. The mass, you know, is 3 kg. This is unknown. You come here, this is the very unknown. The weight, you have the mass you can get. The tension is that. So basically, you have a challenge here and there, which is here and there. So that's why I say you have tension and acceleration as unknowns. So you can solve this simultaneously because you have 2 equations, equation 1 here and equation 2 there. All right. This also applies to the second scenario. Let's have a look at the last one, where You have two objects. The mass 1 here and the mass 2 there. And the whole system is going down. We can get the force diagram or free body diagram for mass 1 and mass 2. Now let's see what's going on here. The system is going down. And obviously we have a tension there. So here is your tension. And here is your weight. And your weight is greater than the tension because the system goes down. Therefore, weight minus tension, it will give you the force that the object experiences down there. Now, for object 2 there, we have the tension here and the weight. The tension is greater than the weight. Therefore, tension minus weight is equal to the force that is experiencing down. It will be tension, the weight is mass 1 times 9,8. Acceleration there. For this one here, we have mass 2, 9,8 minus tension is equal to mass 2 acceleration there. Now, note that we don't have that. We also don't have that, which is that and that. So this will constitute equation 1, and that will constitute equation 2. This again, once more, there's a mistake here. Supposed to be a minus sign there. So, tension minus the weight. Let's give this weight here 2 kg and give this weight here 5 kg. This will be tension minus 2 kg multiplied by 9,8 is equal to 2 kg. Acceleration for equation 1. For equation 2 to be 5 multiplied by 9,8 minus tension is 5 times acceleration going back. This is the same acceleration as that. And then that is the same tension there. So you have equation 1 and equation 2, which can be solved simultaneously. And then you have a number there, you have a number there, you substitute, then that's it. And that will be enough for today. for this section anyway. Thank you for taking a view, and please subscribe so that you can get info when new videos are introduced.